Let's now define the second derivative of a function. If we differentiate a function once, we obtain dy dx. So for instance, if y is equal to x raised to the power 4 plus x squared plus 5, it need not be this specific function, can be any general function. But if we differentiate y once, we obtain dy dx, the first derivative of y, which will be 4x cubed plus 2x, derivative of phi is 0. Now if we differentiate once more, we would obtain the second derivative of y, which we denote d squared y dx squared, which takes the value of, we need to differentiate dy dx once more, we'll obtain 12x squared plus 2. So by differentiating a function twice, we will obtain the second derivative of that function. So let's consider another example. So if fx is x raised to the power 5, for instance, by differentiating the function once, we'll obtain f dash x, which is 5x raised to the power 4. And if we differentiate the function once more, if we differentiate f dash x once more, we'd obtain 20x cubed. So by differentiating the function twice, we obtain the second derivative of that function. Let's define stationary points of a curve. Here we've drawn a curve in blue and we want to define stationary points. Now before we do that, let's make a few observations. We see two turning points. This is one turning point right here and another turning point right here. Why are these called turning points? Because a function reaches a maximum at point 1 and then it decreases to the left and right of that point. Point 2 is also a turning point because at point 2 function reaches a minimum. To the left and right it increases beyond this minimum. So those two are two turning points, and we also here have denoted what we call a point of inflection. To the left of the point of inflection, we see the curve is concave down, and to the right of the point of inflection, the curve is concave up. So clearly at the point of inflection, the curve changes its shape from concave down to concave up. So points of inflection are defined as points on a curve where curve changes its shape either from concave down to concave up or concave up to concave down. So what are stationary points? All turning points and also all points of inflections are stationary points. Now we can see to the left of the maximum, the gradient of the curve to the left of a maximum is positive. The gradient of the curve to the right of the maximum is negative. So by observing the gradient of a function to the left and right of a stationary point, we can determine if it's a maximum. Likewise, we can also determine if a stationary point is a minimum by considering the gradients to the left and right of the minimum point. Gradients to the left of the minimum point is negative. Gradients to the right of the minimum points is positive. Now we see at the point of inflection, to the left of point of inflection, the gradient is negative and it hasn't changed its sign to the right of point of inflection. So how do we then determine what is a point of inflection? At the point of inflection, the second derivative of the function is 0. So by checking the second derivative of the function, we can determine points of inflection. Now at maximum points, the first derivative of the function is 0 at a maximum. Same can be said about a minimum. The first derivative of the function is 0 at a minimum. And the gradient to the left of the maximum point, as stated before, is positive. Gradient to the right of the maximum is negative. So we can test whether a point is a maximum by checking the gradients. Same can be said about the minimums. Now we could also do a second derivative test to determine if a stationary point is a maximum. At a stationary point, if the second derivative is less than 0, then that stationary point is a maximum. If we evaluate the second derivative at a stationary point and it is positive at the stationary point, then that point is a minimum. So we could check if a point is a maximum or minimum by using a first derivative test or by using a second derivative test.